basically, that's all I just said. We're just going to concentrate really on the thought behind the samples. I'm going to break it up into each individual location, so it'll be a lot easier for us to follow along. Your presenter, Scott.
Where was that thing there?
You've seen them before.
I've seen them before. I'm my glass house.
So this is all about me. This is the me page. My degree's in business, but I use marketing as the emphasis, so all this presentation stuff really, marketing really helped me get some of this stuff done. But I started out really as a recycling driver on the City of Orlando truck. Just did recycling, and after I saw, I think it was probably 4 months in, I was part-time, or temporary, and I was able to apply for anything that came in with the City of Orlando, and as soon as I saw a full-time position, I got into wastewater, and at that time it was an apprentice program. So you had to have a B, the Journey Athlete program, and they got me in full-time with the City of Orlando. So I got through that program after 3 years, got my B, became a supervisor there, worked in the safety program for 2 years as the safety officer with Water Concert 1. And after I left Orlando, I came over to Seacoast, and I worked nights basically on my whole career in Orlando and with Seacoast. And my duties as a nighttime operator was the lab operator. So the 3 years in Seacoast, I spent just running all the samples, everything that Christian would run now. You guys meet Christian yet? He's a new guy. He's with Wild Pine Labs, so this is a first-time introductory training for him. So that's me.
What are your hobbies? I don't see hobbies up there.
Not yet.
What's
This is basically how the day's going to work. We will have altered between 11 and 12. We're going to do lunch, so I would say right around 12. So our break is going to be a little altered. All I need is contact time, and instead of going out for lunch, I could count contact time since we're eating in. Nice. So that's great. So it's all right. I'm going to stop right around 12. This watch is fake. It's actually for show. My batteries are dead, so you guys might have to help me out with the time.
How fast we want to get out of here?
Yeah, speed it up real quick.
So
that's today. This is all that we're going to cover, and throughout there we're going to have I like to do the exams along the way to kind of break it up. And at the very end, we're also going to do a group activity. So we'll break up into groups, probably groups of 5 or 4 as it looks here. And then when we break up the group, we're going to spend a good time going over some group activities, and we're going to go over the answers together. So that's the breakdown of the day. All right, why sample? Very basic. Sampling, the reason why we need to sample is to make sure we're in compliance with the regulatory agencies. Because we're regulated in the plant, in the field, by national regulatory agencies, by also state regulatory industries. We have to make sure that we are in compliance with these things at all times, or they can truly get us in a non-compliant state, and then we would have to pay thousands, sometimes more, of fines daily until you get whatever it is right. So the purpose of sampling is that you have to sample, make sure you know what you're sampling for, and then also make sure that you're doing the right procedures. And this is some of the training I'll help you with that. Sampling started out for wastewater and water after the Clean Water Act of 72. 72 is really when it was ratified. It started before then. What happened was the communities had a growing concern about the water quality. And at that time in America, it really started getting popular with clean air, clean water, some of the other issues with our environment. I don't know if you guys have ever seen Inconvenient Truth, but at that time, early 70s, former Vice President Al Gore, he was really young into politics at that time, and he was actually one of the front runners of some of these campaigns that was, going out and trying to get not only air pollution and greenhouse gases back then, but water became available, became one of the things they really focused on. Shortly after this, pre-treatment started getting a focus too, but it all stemmed from the Clean Water Act of '72. Now, wastewater and sampling, here's the Clean Water Act. That's your basic structure is regulating the discharge pollutants into the water streams. They started regulating that, and this is the act that gave each municipality kind of strength and the legs that it takes to enforce actions to people who polluted the waterways. The only exception for the source water is, let's see, it's with permits. This is actually, if you have a permit, this is what started with the industrial pretreatment. So if you have a pollutant from one source through the Clean Water Act, everything was prohibited. And then they decided, well, there's certain things that would be allowed in different concentrations, but people who will discharge those pollutants have to have a permit. And we have permits because as a plant, we actually discharge certain pollutants, but we have criteria that we need to meet. Like chlorine is something we use as a disinfectant, but it's also a pollutant in its natural stage because it goes against, it's not found naturally in the water streams. We actually put that in. So we have a standard that we have to meet on chlorine, turbidity, TSS. Those are some of the pollutants that we send out to receiving streams, but we have a permit that actually regulates how much we can, and that is the NTDS permit. So that's one of the sampling permits that you need. These are where you find your standards. That comes, like you see from the big blue house, that comes from regulatory agencies in Washington. They set all our standards. Now we have, what happened was after these standards were created and we saw the need to actually regulate these pollutants, then the next step was how do you then sample for these pollutants and make sure that you're in your permits, so in your scope of your permit. So this actually became even earlier than the Clean Water Act. The standard method started out in the 1800s. So this is something that really started slowly and then picked up as we got. The need was to standardize the way we started testing. And the book right here, the standard method, became started from paper. Paper was published saying,
I'm sorry, I didn't want her through the door.
see, you're late. A paper came out saying we need to know how to regulate and also test 5 different criterias, and that was in 1889. So that's criteria 1, ammonia. Criteria 2 was oxygen consumption of microorganisms, and then total nitrates, and then the other thing with nitrogen as nitrates, nitrogen as nitrites, and then at the end of the report, the paper, that was the results of the person that came up with this paper. It was actually an organization. So we had the national, actually let's go back. The chemical section of American Association for Advancement of Science. Big name. They're the first ones, the first organizations that actually started with sampling. It eventually became split into different organizations, the APHA. That's one of the organizations that started out from that group. The other one, which will come up in the next slide, through their work, they developed the standard meth book. This 2005 is the current one. Every once in a while, they see needs to actually go through the standards, the methods, and decide that we need to adjust this or that, or there's new information that comes out with testing. I'm going to leave that up there. You guys can take a look at that. Now, one thing that we do, wastewater and water, we try to keep everything, when you do your testing, uniform. So then you know your results are going to be pretty much the same as the next person's results if you keep it uniform. This is the reason for the standard meth. In 1905, that was the first standard meth. If you guys ever find it on eBay, grab it up no matter the cost. It is worth a fortune if you can get your hands on the standard meth #1. And if you're very benevolent, Tom Vaughn might even pay you a fortune to have it in his hands. He collects those. So, standard method #1, keep an eye out for it. These are some of the associations that broke up from that one long-named association. These are some of the splinter groups that started with it. And then, of course, for us in Florida, we have certain other associations. But these are actually the people that all of their information is what you'll find in the standard method. They work together to get that standard method both updated and created. Some of the other resources you'll need for sampling. You use the Sacramento book. That's the one on the right. There's also some other handbooks available. All right, let's start our questions. Who's got a good answer for this one? What association was credited for providing the report that most directly led to the creation of the standard method? The one out of these three.
C, American Public Health Association.
You sure? Final answer.
Yeah.
All right. Anthony, you are the winner. I got 5 of these a day.
Outstanding!
Don't forget your instructor if you win big.
Pay attention.
All right, #2, Clean Water Act.
72.
72.
D, you say D.
All right, 72 it is. Not every question. I don't have that kind of money. All right. What's the first 5? Just one. All you need one of the 5 parameters you're looking for out of this.
C.
All right, show the nitrogen. Very good. And they really just, that paper only focused in on the first 5. And at that time in the 1800s, it was very groundbreaking information. Okay, we're going to go over some terms. These are some of the terms that the books are yours, so you can write in it. Any kind of notes you need to make, these are your books, just so you can keep this information, especially the guys who are going to be taking their exams. This information will probably help you later on. All right, calibration. Calibration, this is all it really is. You're measuring whatever device you're using to test. You have to make sure that that device is going to give you an accurate reading. So that's the instrument calibration. You'll see that term quite a bit. A blank sample. A blank sample is usually DI water because that is clear and pure and free of any pollutants. The color is clear. You don't actually have anything that's going to interfere with your sampling instrument. So it'll give you a true 0 if you use a blank. Or actually, if you use a blank, it'll give you compensate for any impurities. So it's not a true 0. That's actually different. A 0 sample. Let's say you're taking a sample from a chlorine contact chamber. That sample is generally clear, so you really don't have to worry about too many interferences. But if you're taking a sample from a lake, what the meter is looking for a comparison of one source water to another. So if you take a sample from a lake, you may want to take a blank sample first, and that's what a zero sample first, where you're compensating for the actual color of the source water. And that's what's called a zero sample. So now your instrument knows that this is the normal color of the water. If I see another color, then that's the color I'm going to report in the number. Which leads us to amperometric. Is that right?
Amperometric.
Good. I have a tough time with some of these words, so let's work it out together. This sample method of sampling is an electrical method of sampling. You're going through your electrical currents that's flowing through the sample, and it records the voltage. So what you have then is, in most cases with these samples, the lower the voltage, the lower the reading is in milligrams per liter. So if you're starting out with a sample, let's say 100 milligram per liter sample, is going to conduct less voltage or more voltage than a 50 milligram per liter sample. Just really depends on your instrument. So that's what the amperometric, there you go, this sampling method is. So there's several sampling methods, that's one of them. All right, colorimetric, that's the ones we're most familiar with. This method of sampling, you put in your sample, you blank out your machine with a DI solution, then you add your zero sample, which is the color of the actual source water. And now when you put in what's called a reagent, we'll go over that later on, it reacts with whatever's in the water, and that gives you a certain color. Now this instrument will actually tell you, because of this specific color, now you have an X amount of milligrams per liter, or whatever the units it's reading. Pass one of these around. This is color fast Orion meter. This one is a handheld. Before they used to be really big and clunky, but this is one that does the same thing. You know, pass this over here. Yeah, you don't really need to. There's no reagent in it or anything, so it's not going to give you a reading. But I just want you to take a look at what it looks like. Then I've got one over here, which is the same thing. It's a pocket chlorine meter. This one will read chlorine. The higher the color in this instance, the more intense the sample is. And that means it's a higher concentration of the sample. And it's only reading color difference. So it's very important that you actually make sure you zero out the sample before you actually take it, because any color interference is going to give you a higher reading, then it's not a true accurate result. Photospectrometer, that's the actual instruments that you guys have. The instrument is doing the colorimetric method, but that's the actual instrument that you guys are passing around. Okay, reagents, those are the things that react with the water, or whatever the sample is that gives you the color. So that's what we call reagents. There's several different types of reagents. Most of them are potassium-based. There's the chlorine reagent. So they come in very small packets because you really don't need too much. Mostly, you're talking about 5 milliliters of sample, 10. And that would be right around here. And that's really about all the sample you would need, so you don't need too much of a reagent. All right, let's pass the chlorine reagents. These are pillows. The reagents, the chemicals inside the little pillow pack. So you just have to cut it out, you put it in your sample, it'll react with the water, and it'll give you that color. A buffer is the capacity of whatever the solution is to react or neutralize the acid. That's what a buffer is. A buffer is trying to make an acid a base. So whenever you put a sample or a buffer into a liquid or a container, all it's doing is taking the amount of acid and adding more hydrogen to it to make it basic. So the stronger the buffer is, then that's the more hydrogen ion going into that sample, and it's going to make it from acid to a base. Endpoint. Endpoint, this is one of the methods of sampling is called titration. Titration is where, that's over here. Titration is where you use a strong chemical, and it's an acid, and it makes whatever that solution is, goes down in pH, the power of hydrogen, pH. It makes that pH go down into a certain, we're looking at, for most endpoints, is 4.5 endpoint pH. That means when you have enough acid into that sample, and that sample is measuring pH that goes to 4.5, then you're done. That is your endpoint. So that's all that means. Endpoint pHs do vary, but for most samples in wastewater and water, your endpoint pH is going to be 4.5. So you keep adding that acid by titration. And I'll show you a little later on what a titration is. Actually, I think I have one here. This is a two-stage. I don't know if this is going to fit. No. What you would do is one end will go actually in here through the stopper. And if this had hydrochloric acid, that's generally what we use, we would actually drip it into the sample through this, and then that sample will get to our endpoint pH. So I'll have to, I won't do one of those tests, but that's what a titration, what you would use for a titration test. I have some more slides on that later. All right, you guys are making it all right. This is the driest part because it's really, you have to learn some terms in order to get into the rest of it before you actually can experience the rest of the sampling and the procedures. You have to learn some of these terms. So distillate, that's condense of a portion of the sample. So the condensed portion of a sample evaporates. This machine on your this side here, you would have a heat source underneath it, and then when whatever liquid is in here, would the steam of this liquid would rise. Once it cools off, it drips into this side, and this right here would be your distillate. This will be your whatever your condensed material is on this side.
So like moonshine.
Yeah, actually, that's exactly how they do it. And it starts with the heat source. You have to have the heat source, and this apparatus here traps the steam, and you're really using the condensed version. That's the distillate. Aliquot is just a portion of sample. Most people just say, can I have 10 mLs of a sample? When you're asking for a little bit of a sample, that's an aliquot. All right, meniscus. We have it in our bodies, but in sampling it's completely different. In meniscus, you have two ways of reading a meniscus. It's the actual curved surface of the liquid. Basically, when you're pouring in a liquid into a vessel, because it's friction on each side, it curves one way or the other. If the liquid is water, it's going to curve up. Curve down if it's water. So you're reading the very bottom end of that sample. You'll notice it'll curve down, and that's you're seeing that it's water, so you're reading the very bottom. Now, if the liquid is mercury, which we don't use except when they used to have the mercury thermometers, and that's the only time. Right now, no one uses mercury anymore. You're going to read it from the top. It'll kind of bubble up, and you're reading from the top. You don't want to read from the bottom of a mercury sample, because then you're getting the wrong number. All right, we have two basic types of sampling. First type of sample is a graph sample. The graph sample is when you're taking one single sample, which is going to represent a certain amount of flow. Let's say we're at high flow in the plant and you need to take a graph sample. You're only doing one. You're just going out and taking another sample with a dipper. That's what they have over here. This is a dipper going into the bag. This sample is probably something that's going to have to, it may be fecal. That's what we use those bags for, but it's a sample that needs a neutralizer. So the graph sample, what you're doing is one single sample over a certain period of time. That's all a graph sample is. And then the other sample is a composite sample. The composite sample is when you have the need, let's say it's a high flow situation, and you have the need to take more than one sample to actually have a representative sample of the location. Sometimes you may need more than one sample because you're only going to see the low flow or the high flow. Sometimes you want to see a whole day's worth of sample in that one location. That's a composite. So a composite, you can take several different grabs, or you can set up an automatic sampler like they have there in the picture, which automatically will take an aliquot, a sample, over a certain given amount of time or a certain amount of flow. All right. Composite samples, these are some of the composite samples you can do. Flow proportionate. Let's say after 1 mgd of flow that goes past this one location, I want 20 mLs of sample. That's all this is going to be. After another mgd goes by, I'm going to pick up another 10 milliliters of sample. And that's a flow proportionate sample. Now there's time sample. The time samples are different. You're saying at this certain time you want to take a sample, and then you're doing a graph on that. Sometimes if you're using an automatic sampler and your flow proportion isn't working, you want to take one sample every hour, or you know that between 9 and 10 o'clock you're going to have more flow. You're going to want to take maybe 2 samples in that hour, so you'll set it up to be taking 1.5 hours. So that's a time composite sample. All right, reagents, those are the things that we use to react to the water. These are some of the common reagents. These are some of the acids you use in titration. Alkaline solutions, those are also can be used basically for colors. Whenever you need to do a color titration, you would get an alkaline solution, you put it in a substance, and the amount of color that's created by that solution is what you're reading. And that's different than the alkaline solutions, because the other solutions, the acid solutions, you're usually using that for endpoint pH. All right, buffers. These are some of the things that we use to calibrate equipment. For pH, you use buffer solutions. This is a known standard. Every time you pick up a buffer solution that's in compliance on the date, you know that if it's blue, usually it's 10. We try to keep it standardized in America. So blue, you may see clear, which is usually 13. You know every time you pick it up, you read the label, it says that it's in compliance with the date. That's the buffer you expect that's the actual value once you measure it. Scales, they take regular weights where you actually have to put on certain milligrams or pounds, and then you can actually calibrate your scale through that. Turbidity, they have NTU standards and they have formazine standards. We'll teach you that later, but basically you're saying every time you put that in to calibrate your turbidity meter, that you know once you read on that label it says this is a 10 turbidity, it should be 10 turbidity when you put it in your sample in your machine. So that's what you're calibrating it to. All right. Portion of sample? Big. All right, let's see. An aliquot. Sodium hydroxide. Which one is that more? An alkaline solution, an indicator, a buffer solution, or an acid? Sodium hydroxide. Okay. There are a lot of B's, a lot of A's. It is an alkaline solution.
Give Bob a ticket.
Alright, this one I need a hand for. Two types. What are the two types of samples we do?
C.
I saw Dave's hand. What did you say, Dave?
C.
Alright, Dave, you are getting the second of these wonderful things. See, now you guys know that I'm
3 days, 2
completely
nights.
addicted to these
I know
things.
when he wants to give it out, he says he needs a hand. Raise your hand. That's what it is.
That's it. Composites and grabs, very important because in the permit, and the plant permit, it specifies that this sample has to be either a composite or it has to be a grab. And if you do one for the other, you will be out of compliance. So you have to make sure that you make sure you read your permit, you know what you're looking for. And we'll go over that in the next session. All right, buffer. That is the measurement of the capacity of a solution or liquid to neutralize an acid or base. True. A buffer, all you're looking for in a buffer is you want to see that acid go up to a base or the base to go down to an acid. It's a neutralizer. It'll do the opposite. Okay, let's get some lunch going. Hey, lunch. We have to corral the smokers very well.
Where are the smoking areas? That's what
To transport your samples, to collect your samples and to transport them from one side to the other. Different, various sizes and various actual material. So it just really depends on what the sample is. There's some samples that react to plastic, so you can't take samples that are, you can't use plastic. You have to use glass. Some of these vials that we need, they're not only for collecting the samples, they're for running the samples. So like pH, it's better to actually use glass for pH than not. pH though is one of those things that we measure in 2 digits, so it really doesn't, it's not too far off. So I'm going to pass this around. This is a 1 liter bottle.
How do you make it?
You notice that in this one, there's no markings. So you're not actually being precise with this bottle. The only thing you're looking for is to collect the mark. Here you go.
That's for long highway drives for someone that portable cars. I can feel it like the right time. Let's go this one.
Yes,
Not just come. I have to build this. Where are they going?
all right, you're around that, that's yours.
From the ground back out.
Now, there's smaller containers here. These smaller containers are generally what's being used. That's like this one over here for your actual analyzer, your whatever you're using to sample. This one is for chlorine, and it's geared to fit specifically into the meter. So you're not going to use this to grab a sample. You're going to use this to run a sample. Some of these samples, you'll see caps on them, and just about all samples have them. Either it's for mixing your reagent at the site, or it's just to keep it where it's not going to get any contaminants going into it. So this cap actually has where you can sign and date, and it's kind of a chain of custody where you're picking up your sample, you know who got it, when it was taken. It's going to be refrigerated any other day. You come back, you pick it up, you say, all right, this was taken this day, this time, and this location. Those are generally the information you're looking for when you're labeling your bottle. So that's collecting and transporting your sample. Beakers. Beakers you're mixing, and you have a volume of sample you're looking for. So like the last one I passed around is really blank. The beakers now, there's plastic and glass. They have actual graduated markings letting you know what it is. Now, there's usually the higher the glass, more accurate than the plastic, and there's different grades of beakers. A grades mean that it is precise. It is accurate. Whenever you put in a sample and you're looking at your meniscus, whatever it says 40, it's truly 40. It's not about 40. The plastic are the ones that are not as accurate. So they're telling you it's right around 40 mLs or 50 mLs, whatever the case is.
If they're not exact, why are they allowed to be used?
They're only used for if it's for recording a sample that you have to actually record or report to DEP. Then you're going to use one of the accurate ones. If it's a sample that's just a process control sample or something that you don't need an accurate measurement, then you can use that. Or if it's only a container that you're going to be siphoning out of something from a pipette, you may only need an accurate, roundabout amount. And then the pipette is going to give you your accurate amount. And we'll go over some pipettes next. So the graduated cylinders, call it graduated because it's actually going up instead of out. Again, you have your plastic and your glass. So there's actually two grades of glass, A and B. And when you're really measuring finer things, you have to use your glass cylinders. Plastic is really, you can mix with them with something like one of the longer pipette tips. So you can actually mix with them like that, and then you're just pouring out your sample. But this is a 500 mLs. Generally, you're only using the sample or something this big if you're running a solids test. You don't really need that. In the grand scheme of if you're going out and sampling, you're not going to take this out for a sample to collect your sample with. You're going to take one of these out, you're going to collect your samples with this, and then you're going to pour it into one of these when you're ready for your accurate measurement. And again, when you're reading your meniscus, you're holding it up, and you're looking at the liquid level. If it raises, it's mercury. If it lowers and dips, you're looking at water or water substance. And you're holding it high level. You don't want to try to get your sample looking down at it, because that's not going to, it's going to short you. So you're actually holding it high level. Alright. Those common measurements, 5 mLs, the real small ones, to 4,000. Those are the ranges. I don't think we have much more than 1,000. That's our biggest one that we keep. Now pipettes. There's several types of pipettes. What it is now pipettes are using to deliver smaller amounts of sample into a container. This one is a precision pipette where you can actually dial in right over here what exactly you want as far as your milliliters. This bulb and pipette here is an old-fashioned one. There's a suction side, and then there's a discharge side on the back end. So what you're doing is you're holding in the ball, and that's how you're going to create your vacuum, your suction. And the tip on this side is going to be inside here. And then you just actually let go of the ball, and the air from the top is going to just blow out your sample. And there's a line over here. Now when you actually get your liquid to that line, that's 5 mLs. When you get to the line, you're not taking it all the way up, you're just going to the line. Now this takes the place of this, so you actually dial that in, and we got some pipettes here where it's not graded at all. You can't really tell what it is here. But this is the tip, so the pipette itself, once you dial in a number and you suck up the liquid, there's usually like a stopper on top of the pipette where you go down to the stopper and don't push anymore, or else you're going to get more than the sample you need. You just push down to the stopper and then you suck it up into the tip here, and the sample is now exact from whatever you have the pipette, and you deliver it into a beaker, and that's how you do your test.
So those have to be calibrated?
No, because it's the dial situation, but you generally, any lab equipment, you usually do an annual calibration anyway. And for those pipettes, what you do is you actually hold it against another, 1 ml, whatever the pipette is, and then you can either fill that beaker to whatever that known value is of milligrams per liter, and then if the pipette sucks it all up, then you're calibrated. But there's no actual internal where you take it to the factory and the factory calibrates it and bring it back, unless it's a digital. Digital, that's different. Those you pay half, and that's extremely pricey. Something like this pipette, generally you're looking about $300 for a pipette like this. Something like this is disposable. You're getting that for $5, if that. You probably get a pack of them for about $5. There's different types of flask. There's a volumetric and an Erling-Meyer flask. That's what I have over here. I don't have a volumetric flask to show you guys, but same thing. This is just for mixing. It's graduated. This one is a graduated one. It has a tip because it's for suction. This is one of those that's a suction pipette flask. You would have to put a funnel in here with a stopper, and you're putting the sample inside the funnel, and you're actually going to be vacuuming out the sample, and the discharge goes in here. So at that point, you're actually going to be measuring whatever that pad is in this sample. I'll show you that later. All right, we went through part of this before with the titration. The glass burette, that's what those are. It's actually where you're delivering the sample, but the burette is different than the pipette because you're slowly filling it up from the bottom up. And then after you get your burette, you're releasing it a little bit at a time. So usually it's droplets that you're releasing into the sample. You can open it up for a faster pour, but generally when you get to the level that you need it to be at, if you're doing a 20 ml sample, you might just open it up until you get to 15 mLs and then start dripping it back until you know exactly you're at that 20 ml. These are some of the brushes we use to clean test tubes over here. Generally, if in wastewater or water, when you're using a test tube, you're looking for a solids content. There's different types. There's a cone test tube. Those are usually solids you're looking for. So test tubes, there's test tube caps where you can actually cap it up and shake whatever you need to make a reaction. And then when you're done, of course, you have to clean it out. This one is a very simple cap. It's not airtight, so you actually have to hold on to it. But you're only mixing maybe 10 mLs out of this. And you're not really, or even less. That would probably be the max you'd use to mix out of this one. All right, stirring rods and stoppers. Stoppers generally fit in any of these type flasks. Some have one hole, some have two, just depending. This is a stopper that is specifically for titration. That's why it has the two holes. And then when you're using a funnel with a stopper, you actually have to fit that in, then it goes into the glass bottle. And that's for some applications. So stoppers are very important. They're small, but you actually use them quite a bit. The Parafilm here is something that you use. It's a very thin layer of I'm not even sure what the material is. Would you know? It's just plastic, we got Parafilm. It's kind of like a stretchy plastic, and it's almost like the shrink wrap, or even like a saran wrap, but it's just tighter material. And once you put it on, you seal it up, it's actually pretty good. In most cases, hold it upside down, and you're not going to get any leakage. It's a lot cheaper than having a cap or a stopper. Was that right?
I said that you wouldn't want to.
No, generally no. When you're doing those, you're only doing like a quick one or two. You're not going to hold it over there and over somebody's head. Yeah, we frown on that. All right, what do we have here? Questions? Flask, used for containing and mixing chemicals and samples.
True.
True. Yes. All right. What sampling tool is used to measure volumes of samples, usually from 5 to 4,000 mLs, more accurate than beakers? Look at Filbert.
C.
Graduated cylinders. It's graduated. Glass is definitely more accurate than plastic, and it's graded. Did I get you ready here, Filbert?
For what?
All right. Look at you.
What? Ticket. Oh, no, I didn't take it.
All right.
I've been hoping.
I got Anthony on.
Well, that was pretty easy. Thanks, Sean.
That was an easy question. That was a given.
Shame to get it thinking about that.
What lab tool is used to deliver small samples? Rana and Thomas.
D. Pipette.
Yes. You're 2 in a row this time. Look at this. All right, I'm done for this hour. All right, you guys are done participating. Let's go through. This is part of the sampling plans. What we have is when you know you have to sample, and it's something that you're looking at your permit. Let's say you've taken over a lab, you've taken over operation, you got your actual permit in front of you. You know that you need X amount of samples that need to be taken. The next thing you need to do after that is a sampling plan. You're going out to where's the one that has the chlorine? The 518? Yeah, especially you guys are going out there, you know there's a sample that needs to be taken. If you're going to do your chlorine, usually you don't have to take samples there because it's just for algae, but if, for instance, you want to take a sample there, you have to have a sampling plan. We do walkthroughs. Walkthroughs is basically when we're going from one area to the next to pick up our samples. Thank you. I'm going to get a few of these from time to time. It's going to go for posterity, and you might see yourself in the director's report. All right. Sampling plan. You know that you have to take your samples. You're going to be going through the plan on a walkthrough. Every plant should have one. These are some of the things you're looking for. When you're taking a sample, you have to figure out what size bottle you need to take the sample so you don't get too little sample and then have to go out again to get that sample to make sure that you run enough for the test. Now, the way you determine that is by reading your O&M on your actual meters. Each meter needs a different amount of sample in order to get an accurate reading. So when you look at your meter, it tells you I need 10 mLs to run my sample. You want to go out to the plant and get at least 20 to 30, even 50 mLs so you have extra sampling. So you're looking for the size of bottles you're going to need. You want to get a representative sample by location. So let's say you're in a, let's use this to represent a tank. This is a tank. Let's say it represents a tank that's 20 feet down. if you're taking your sample and you want a representative sample of this actual location, the best place to take it is dead center, at least 7 feet down. That'll be the best sample location for a sample this tank. Now, if you are running an influent and effluent, let's say the tank goes this way, then you don't want to take it right at the front of the tank. You want to move down a little and take it maybe 10 feet in, and then same thing on the effluent. Take it a few feet out, and try to minimize as much of the disturbance as you can. You don't want, you want to take it in the area where there's mixing. You don't want to have it in a still area where there's no kind of mixing, but also you want it in an area where, especially samples that are intolerant to turbulence, you don't want to have a sample that's going to be, those are TSS samples. You don't want a sample that's just going to keep running around and rolling around the water, rolling around where you're going to have, you're not going to have an accurate description of what that one location is.
Why 7 feet down, so?
Well,
it's 20-foot tank deep.
Generally, you're looking for just about half. You could go 7 to 10 feet. If you're doing 20 feet, it's really because of the turbulence, because it's not going to be a steady, stable tank where you're going to have just no influent or effluent unless the clarifier, then it's different. But you're looking for anyway just about half or higher.
Average. What average?
So you're looking at average.
I was thinking half, that's why I asked.
Yeah, half will be fine. But you're looking at just about half or higher. And some tanks, when you get lower, you're going to get some settling. So you're going to get more solids than you really want, and then you'll end up having to filter that out. They need you, Jeff. Is it the baby?
No.
Just Gary.
It's a girl. Yeah. You're turning it off, sorry.
All right. Well, the sampling plan, one of the other things you need to know is what's the good time to take your sample, especially if it's a grab sample. So if you're looking for a sample that is going to represent your flow, you're going to get your peak times. Our plan is flow equalized, so it's not going to be as important. But generally, if you're running a sample plan, you're going to be thinking that thought: where's a great location? What time should I take the sample? How much sample should I take? Now, what method of sampling are you going to be using? That's the colorimetric method. Remember that one? Those are the certain things that you're also going to add into your sampling plan. Now, these are some places where you can actually find sampling plans. And the one wastewater book, this one here, I believe is book 2. Book 2 or book 3 of the B course. Well, book 2 of the B course. There is also, in the standard meth, I don't have it there, but standard meth also has that. So if you need to find something with a sampling plan, get you an idea of thinking about what you're going to do for your sampling, standard meth has it. The DEP site, they have it as well. There's a whole big section on the DEP website that has lab and SOPs for labs. And one way after you make your sampling plan is you want to do an internal audit, just so you could make sure that whatever you have created is going to be not only feasible, but also going to be convenient for everyone. And areas that aren't safe, you're going to review all that things when you're doing your internal audit, and then just change whatever you need to change after you do your internal audit. All right. Now, this is also when you're going out, you get your sample, and you're coming back. You want to figure out what lab test needs to be done. Now, before you get any of your samples done, you have to take care of your lab. Make sure your equipment's clean, make sure you can get in and out, you know where things are, because some of these samples are they have time elements. So you have to make sure in a certain amount of time you get them done. And if you're spending your time cleaning up the lab, looking for things, trying to locate them, you're not going to be able to get your samples done on time. And if your meters aren't calibrated before you get there, that's also going to eat up some of your time. So the best thing to do is start your calibrations before you even go out on the plant. And then when you get your samples in, you're ready to run your samples, you know where everything is, it becomes a lot easier for you now to do your samples. So how many guys are real familiar with plant walkthroughs? Yeah. We got a few? All right. Now when you do your walkthrough, Brad, since you do them often, do you get in your mind like a pattern or a round, or you just
You want to have that order to what you're taking your samples.
yeah, so you're basically, Scott, I know you normally do, right? Whenever you're taking your samples, you got
I
a
got a routine like
routine.
a robot. I do the same thing, the same time, everywhere I go.
Yeah, it helps you get your thoughts. And
Why
then
there's that 30-minute nap?
25.
he's been cutting back.
I wasn't sleeping well at home.
Makes them crappy. It's one of those things where, especially if you get used to going through the same patterns all the time, sometimes you may overlook something. So it doesn't hurt to switch it up. But when you're actually running your samples, you want to run the chlorine first. So that's the last place you're going on your rounds. But when you're on your rounds, you're also looking for some other things. Not only are you checking out the plant and the equipment, but there's some interferences that will affect your sample if you don't actually notice it. Let's say you're going on your rounds and you notice that this tank is a little lower than usual. I mean, that might not be the right time to take that sample because something else is happening upstream and it may not be representative. So you always have to look around when you're doing your rounds, grabbing those samples. All right. So I was saying about you preparing to run the test, observing your surroundings when you're grabbing your samples. That's a big thing because I remember, like I told you guys, I started out in the apprentice program, and I had several of my lead operators at the time who, they basically, what they would do is just give everything to the new guy, you know, and especially in our apprentice program. We had training outside of the workplace, so our training, we were gung-ho, we were ready to do it. So we were the ones who did the rounds, we were the ones who actually grabbed those samples. And I remember there was one time that I go out and I'm grabbing a sample and something just didn't look right. And I go back and I'm checking it out, and it was a lift station, was turned on, but it was sending us too much flow. And the tank just looked higher. And if I were to grab that sample, then it would have been not a representative sample. We could actually have gone out of compliance in whatever we were testing for. I can't remember what it was at that time, but just because we were getting more flow than we needed to at that one time, then I would have grabbed that sample, and that snapshot in time would have been just enough to get us out of compliance, possibly. So it's very important that when you're going out and looking at these things, you question it. If it doesn't look right, that's not the best time to take your sample. You know, your goal in your sampling is to make it representative, make that sample reliable. So whenever you have to go back and if the EP inspects this and says, let me see your lab records or whatever it is, you can actually feel that each sample is being taken, and you can say, this is my representation at this time.
I got a question for you. If you're taking a sample that's time sensitive, like, you know, you've got 2 o'clock rounds, so you need a sample at 2 o'clock, and something isn't right, like you said, what's the procedure on that? Do you skip that sample and try and solve the problem, or you take the sample anyways and take that into consideration? Or?
Yep, solve the problem, because anything that we do with DEP, they themselves, most of them are in our background in wastewater and water, and they know that things happen. Let's say there's a headwork sample that you need to take at 2 o'clock, And at that time, the field, they're having some trouble with that station. And you're either getting too much flow or too little flow. At that time, even though it's 2 o'clock, you shouldn't take that sample. You write a note in your logbook saying that at that time it may not be representative, you'll do the sample later. And that's, the logbook will take it. But that sample is, the activity in the plant isn't lost because you have, in that particular location, you would have an auto sample that will be picking up. So it's not that you're trying to escape the system. What you're doing at that point is you're getting a representative sample. And your representative sample would be when your conditions are back normal. Because things like that, it happens all the time. Now we set an outline that samples should be this round 9, the other round 2. That's your guideline. But the guideline is just that. It's only a guideline. It's not a mandate. And the mandate is different. Let's say you have to do an hourly grab, and you took the grab at noon, and you're coming up to 12:58. You ran out of time. Now you're among the mandate. You got to take that sample, no matter the conditions, because you're going to miss that hourly grab. So that's the exception. If you have a mandate, that's what you got to do. You're mandated, you got to do it. If you have a guideline, then you write it down, you explain it in your actual logbook, and the DEP personnel, they know that. They look at the logbooks, they look at whatever we write down. When we take samples, we actually write notes of our samples. So for anything that's regulated. So that's basically how you would do it, your procedure at that time.
Who would mandate it? The EP?
Mostly everything for us is mandated by Florida DEP. We have EPA, national EPA standards, but it's all administered under Florida DEP. Like, I don't know if you guys remember, end of last year, we had a sludge situation where federal EPA found something that our local Florida DEP missed with our sludge sampling, and it was the frequency of samples. We should have been taking them more often than we were. So at that point, the federal system took over for where the state system didn't see. So our